Well, I hope you all got a lot of sleep. Unlike me. Right? Huh? Yes. I always get my inspiration at those hours. All right, let's review what we ended up with last time. We were talking about discrete time periodic signals, or in particular sinusoids. And we explained how frequencies around 0 are considered low frequencies. And frequencies around pi are high. And everything in between is mid-range. In particular, the signal xn equals 1 for all n, is the lowest frequency signal of them all, because you can write this as e to the I 0n. Notice, because we're defining things around the unit circle, frequencies 0, 2 pi, minus 2 pi, 4 pi, and so on, are indistinguishable. And so whenever you have a frequency, after you take out all the multiples of 2 pi that you want to bring it into the primary rotation, from 0 to 2 pi or from minus pi to pi, if the number you land is somewhere around 0, then you have a low frequency signal. If it lands around pi, you have a high frequency signal. And everything else in between is mid-range. The fastest varying signal, of course, is minus 1 to the n, which changes polarity at every adjacent sample. And this you can write, how do you write this in complex exponential form? E to the? Is there a difference between e to the negative I pi n and e to the I pi n? Huh? No. In fact, you can write this as e to the I 2k plus 1 pi n, where k is an integer. So any odd multiple of pi is the same as pi in that unit circle. So this is the highest frequency signal. Another important point that I want to remind you of is that in continuous time, there was a monotonic relationship, inverse relationship between frequency and period. So in continuous time, omega naught was defined as 2 pi over p, and there was no problem with writing p is equal to 2 pi over omega naught, so long as omega naught is not equal to 0. Because in continuous time, there is no restriction on the period being an integer. It can be any number, any real number, or in fact, any positive real number. But so there's that inverse relationship. As frequency increases, period decreases. That's it. But in discrete time, we can write omega equals 2 pi over p, but not in general. P equals 2 pi over omega naught, because 2 pi over omega naught may not end up being an integer. Let me put the finishing touch on the discrete time periodic signals with another example, and then we'll move on to another topic. So I want you to talk to your neighbors and tell me if this is a periodic signal, and if so, what is its fundamental period and fundamental frequency? Meatball. Is he here? Ah. Do your gig. Pick somebody. Huh? There you go, Meatball. You are? Misha. What have you got?
I said it's periodic because xn plus p
xn plus p cosine n plus p. Okay.
p is equal to
So you want this to be equal to what?
p is equal to 2 pi k. Because
Okay, but why do you want it to be 2 pi k? Well, what do you have to equate this to? For this signal to be, for a signal x to be periodic, x of n plus p must be equal to what? X of n. So we want to be equal to xn, which is cosine of n. So p must be 2 pi k for some k integer. Okay? You shook your head a bit too early. What's wrong with this? Don't, what's the restriction on p?
it has to be an integer.
Is this an integer?
No, p is 1. So if
Any integer multiple of 2 pi, will this be an integer? Not an integer. Pi is not a rational number. You multiply a irrational number with an integer, you're going to get another irrational number. Yeah. And irrational numbers are not integers. So this is not an integer. So cosine n is not, as much as you'd like to believe, periodic. So we invent another term for it. It is almost periodic. Or quasi-periodic. So in the strict sense, if you take a value, so let's plot this. Of course, we can't plot it exactly. There will be an envelope, okay? And you're going to have these lollipops, okay? In continuous time, there's no issue. At any point in this envelope that you start with and evaluate the cosine, you move by some amount, you're going to get to the top of the next peak. The problem is when you pick, for this kind of a function, when you pick a lollipop here, there is not a single lollipop in this direction or in this direction that has exactly the same height. Some other lollipop on the next cycle will be just ever so slightly to the left or to the right of this one in that cycle. You'll never get exactly this value. But when you look at it from afar, it looks pretty periodic. But it doesn't satisfy the strict definition of periodicity. So that leads us to the question of if I have, so when does a signal like xn characterized by cosine omega naught n let me rephrase this. So for what omega naught is cosine omega naught n periodic. And that's what I want you to think about with your neighbors for a couple of minutes. There's a neat, crisp, clean answer to this question, and I want you to find it. Again, you plug it into the definition of periodic signals, and see under what conditions for omega naught, x of n plus p is equal to x of n. Are you done? Need more time? Who's done? Who's not done? Wait. That doesn't add up to 100%. Do we go back to the situation where you don't know if you're done or not? How many people don't know if they're done or not? Man. I wish you all the best this evening. That's why we have TAs. They can tell you how many minutes you've got left. Then you know you're going to be done at 8 o'clock. Okay, Misha, pick somebody to answer. So his name is We Know That.
Oh, sorry. My name is Ali.
Ali.
So we know that omega naught has to be 2 pi
omega naught is equal to 2 pi over p.
We know p has to be an integer.
Mm-hmm.
So omega naught, this has to be 2 pi divided by
2 pi divided by some integer. Doesn't quite give us the... Yeah. So what does that say about omega naught? Right, it's not wrong. It's just it's not clean enough for me. Why don't we try putting it into the equation? X of n plus p. We want it to be equal to x of n. Okay? So cosine omega naught n plus p must be equal to cosine. Well, this is equal to cosine what? Omega naught n plus omega naught p. And omega naught n. Hold on one second. Omega naught n plus omega naught p. And this has to be equal to cosine omega naught n. That's what we want, because this is x of n. So we want. So what does that say about omega naught p? Exactly. So omega naught p must be equal to some integer times 2 pi. Okay? Which means omega naught is equal to 2 pi k over p. There's nothing magical about this 2. I can incorporate it into k without any problem. K is an integer, p is an integer, 2 is an integer. So what kind of an object am I looking at? What? Rational must be a rational multiple of what? Exactly. So not only is cosine n not periodic, huh? Question? Yeah, omega naught equals 0 is rational. Sure. That's for k equals 0. So cosine n is not periodic. Cosine square root of 2n is not periodic. Cosine m over n times n is not periodic. Basically, your omega naught has to be some rational multiple of pi for the signal to be periodic for these sinusoids. And the same, of course, holds true for, same holds true for sine omega naught n and e to the I omega naught n. They're all in this, they're all part of the same family. Yeah?
So why is it 2 special? I mean, why can't the numerator have to be an even?
Because I can always modify p to incorporate that 2. I can multiply that by 2 and absorb it. It's all a subset of the rationals. Another way to see it is, say, omega naught is a rational multiple of pi. So it's m over n pi. And then look at cosine omega naught n. So you're going to get cosine m over n pi n. That's your omega naught. Right? And now what's cosine omega naught n plus p? What's a p that works for sure? This is going to be cosine m over m pi over n plus m pi over np. You want this to be? A what? What do I have to add to this angle to get the same cosine back as before? Or some integer multiple of 2 pi. So I have m over n pi p equals 2 pi k. Pi cancels out. That's the critical part. You need something on this side so that it cancels the pi on the other side. And then you can ensure that p is an integer with an appropriate choice of k. So p here is what? 2k times so cross multiply and simplify. Solve for p. N over m. Okay? Now, either m and n are coprime, meaning there's no common factor between the two, or there is. If there is no common factor between the two, if they're relatively prime, so it's not like 6 over 4 or 10 over 6. Let's say it's something like 4 over 3 or 3 over 4. They don't have a common factor, so there's nothing to simplify that ratio. Then what value of k would you need? Pick a k, an integer, such that this p will be an integer. What would you pick? Y over n. It can't be m over n. It's got to be an integer. What are you trying to get rid of? The denominator. You pick k equals m. So that's how you show it. You start off with omega being a rational multiple of pi, meaning it's a ratio of two integers times pi, and you plug it in here, and there's always a k that works. K equals m always works. You may get a smaller value of m depending on whether n, capital N, and capital M have a common factor that you can cancel out. Yeah?
But if we want the smallest value of p, then shouldn't it be m over n? Because period is the smallest value of k that will give us...
M over n is not necessarily an integer. You want p to be the smallest integer. Yeah. All right. So that's about all I wanted to say about periodic signals and sinusoids in continuous time and discrete time. And I'll give you a 2-3 minute break, and then we'll move on to impulses. So remember, just to give you a roadmap, I talked about important signals. Recall important signals. If the space of all signals had an alphabet, these guys would be at the very front, the A, B, C, and D of the alphabet. So we've been talking about e to the I omega naught t, e to the I omega naught n, cosine omega naught t, sine omega naught t, and the same in discrete time. So these were the sinusoids. Now we're about to move into the other signals that are important, namely the discrete time impulse, which you've seen a little bit of in action, which is 1 at the origin and 0 everywhere else. We'll talk about the continuous time counterpart, which is beastly at first. This is terra incognita for most of you, because you haven't seen this in your calculus courses. And there's a family of functions related to these. For example, the unit step, which is 0 for negative time, and then it turns into 1 for 0 and above. And there's a counterpart for this. Oh, this one we draw with an arrow at the origin. And we put a number 1, not because the height of this arrow is 1. This one is very clean. The height of this lollipop is 1. Very simple. In this case, the height is actually infinity. The width is 0, but there is non-zero area underneath. And it's that non-zero area which is the strength of this impulse that we'll talk about, and we'll explain that's the strange thing about these so-called functions. And the counterpart for the unit step, of course, is this guy here that's 0 for negative time, then turns into 1 for positive time. Okay, take a break, and then we'll start the discussion with these. let's start with the discrete time impulse. We've talked about this already, but we'll say more about it today. One of the names for this discrete time impulse is the Kronecker delta. You'll see it in some literature. It's defined very simply. At n equals 0, it's 1. And at all other n, it's 0. Fair enough? Shifted versions of these, if my impulse is at integer k, how do I denote that? Delta of what? N minus k. Okay? Now, we saw this once in a previous lecture. You can represent any signal. Let's say I have a signal x, whose lollipop diagram is like so. Let's say this is 1, 2, minus 1, 3 halves, and so on. I can always decompose an arbitrary signal. So here, this is x of 0. This is x at minus 1. This is x at 2. And this is x at 1. I can decompose any signal into a linear combination of shifted impulses. For example, in this case, I can write this signal as an impulse at the origin scaled by what? 2, which is x of 0, plus an impulse at minus 1. I should have done minus 1 first. An impulse at minus 1 of height 1, which is x of minus 1. An impulse at 1 of height what? Huh? Negative 1. And so on. So this is x naught delta n. This is x minus 1 delta of what? N plus 1. This is x 1 of delta n minus 1, and so on. I can always do this decomposition. And so, in general, I can take a signal x and say that I can write it as a linear combination of a bunch of shifted impulses, where k goes from minus infinity to infinity. And if this summation looks bizarre to you, like I said, always write it out, and you'll see the pattern. It's an infinite sum, so we'll put 3 dots and start with the first sample, x at minus 1, delta of n plus 1, just like we had it in the diagram, plus x 0 delta n plus x 1 delta n minus 1. That's basically what that summation says. When you look at a particular sample n, how many terms on the right-hand side are non-zero? I pick my n. Let's say n is 5. How many terms on the right-hand side are non-zero? Ooh. Ask your neighbor. 30 seconds. I pick a number, n. So apparently there's confusion with the question. I pick an n. I pick a value of n. I pick n equals 5. That's on the left-hand side. Once I've picked my n, how many terms on the right-hand side are non-zero? Huh? Which one? For k equals what? 5. So on the right-hand side, only one term. Is non-zero. Namely, for k equals 5. Because remember, the Kronecker delta, the delta function, is non-zero only when its argument is 0. It's when the argument of delta is 0 that you get delta of that argument equal to 0. Where does that happen? Only for one value, k equals n. So this is a property of the Kronecker delta, and you'll see it's also going to be a property of the Dirac delta, where when it comes in contact with a function, it plucks out the value of the function at the location where the delta is active. This delta, the only term on the right-hand side that's non-zero is the one corresponding to k equals n. That's what makes the argument of the delta 0. Okay. So this example shows you how you can decompose a signal in the time domain as a linear combination of a bunch of impulses. It turns out we can also decompose signals in the frequency domain into a linear combination of complex exponentials. And these are the two parallel tracks that we're going to use throughout the course. Sometimes it's easier to look at a signal in the time, entirely in the time domain, and say, okay, it consists of these impulses. Sometimes it's easier and more illuminating to look in the frequency domain and say, okay, this signal can be decomposed into a combination of a bunch of complex exponentials. That's the whole discussion with Fourier series and Fourier transforms that we'll come to later. And that's one of the main reasons why I've been covering the sinusoids in the class. So remember these parallel tracks as we go forward. We're now dealing entirely in the time domain about how we can decompose a signal into a linear combination of a bunch of impulses. Okay. I defined the unit step function. Let's go to another board for that. And the unit step function is as the name suggests. It's constant, namely at 0, all the way until -1, and then it goes through a 1-unit jump. We denote it with u of n. And its description is that it's 0 for n less than 0, and it's 1 for n greater than or equal to 0. Now, what I want you to do with your buddies is to express the unit step in terms of the impulse. And tell me what you get. Okay, who, Ali, were you the last one? Pick somebody.
Hi, my name is Sarah.
Sarah.
Do I just give you the answer?
No, you walk us through. You never give me the final answer. You always walk us through.
Okay, well, is it called the delta? Only gives you 1 point that goes to 1, but you want it from 0 to infinity. So you can do the summation.
Okay, summation.
The summation from,
So this is U of n.
yeah, for you and
Uh-huh.
from k equals 0 to
K equals 0 to infinity.
infinity. You do the Kronecker delta of n minus k.
Kronecker delta of n minus k. And exactly how did you get to here based on what we've said so far?
Because when you subtract the number, it shifts it to the right. And you want it from, and you want the delta t equals 0 because that gets you to 1. And you want it to fit in.
So I'm shifting to 1, as you say. And this is at 0, 1, 2, 3.
Yeah, and if you have a sum of that, then you'll get the unit.
Right, and the scaling on each of these is 1. So here I'm looking at a signal xn, which is U of n. The values of the unit step for negative k here are 0. So x of k, which is my U of k, is only non-zero for non-negative k. So the summation starts from 0 to infinity. And that's why Sarah has from 0 to infinity. And in that range, in the range k from 0 to infinity, x sub k, or u sub k in that case, is what? 1. And that's why all the coefficients are 1. So this is one way of looking at the unit step and its relationship with the impulse. Let's play around with that a bit. So, just 1 second. Yeah. First what? No, the unit step does extend to infinity. And that's why your k has to go toward infinity. You have an infinite number of shifted versions or delayed versions of delta. See, these are all delayed versions of delta because k is going from 0 to infinity. So the unit step is the undelayed delta plus the 1 sample delayed delta plus the 2 sample delayed delta plus the 3 sample delayed delta, and so on. No, U of n is just the signal that I've defined. This is a signal that defines how, in discrete time, you truncate another signal. If I want to truncate another signal so that it starts from 0 and extends to infinity, all I have to do is multiply it by U of n. It shows up a lot. That's actually a good question. Let's draw an example of the situation where, let's say let's say my signal is, I have a signal 1/2 to the n. How do you plot this? Why don't you give the answer, Mark? Yeah, plot this for me, lollipop plot. At 0, it's what? No, forget delta. Just give me a lollipop height. 1. At -1, 2, -2, 4. At 1, 1/2. And so you see it decays on one side, it explodes on the other side. One of the signals that we'll be using a lot of in this class is this signal. The signal that's 0 for negative time, and it's equal to 1/2. So let's call this f of n. It's 0 for negative time, and it's 1/2 to the n for non-negative time. So what am I doing? Compared to this, what is this? It's everything from 0 and to the right. So I've truncated out everything on the left. Well, a clean notation to write f of n is simply x of n, u of n. Or 1/2 to the n, u of n. And of course, if you ever study circuits for analog systems, one of the things that characterizes the behavior of a circuit is what we call the step response, the response to a unit step function of a particular system. And that says a lot about the dynamics of the system. Okay, let's get back to the relationship between the impulse and the unit step. This is one way to write it. Now let me change variables. So let L be n minus k. Rewrite u of n. What would you say it is? If L is n minus k, how do I write u of n? How do I rewrite that summation on the right-hand side? Sum. So what's the variable of summation now? No, variable of summation is one variable. N minus L is not a variable. Huh? L. L goes from what to what? K went from 0 to infinity. N is a finite number. It's an integer. And K is going from 0 to infinity. So where does L go to? Infinity or minus infinity? When K is infinity, what is L? Oh boy, some people didn't sleep last night. When K is infinity, what is L? Why am I hearing N in the answers? N is a finite number. The integers do not include plus minus infinity. The real numbers do not include plus minus infinity. Now with that additional piece of information, which you should have known from Appendix A, what is L when K is infinity? Plus infinity. Negative infinity. And when K is 0, what is N? What is L? N. And I have a delta. Boy, that was painful. Delta of what? L. So this is another way to write it. And let's do the graphical interpretation of this one. So now I have my generic variable L. I plot delta L. So it's 1. This is delta of L. What does that summation say, that last one? So these are all 0 values. If you were to think of the summation as some kind of an umbrella that covers some range of values of L, what would it be? Here's my umbrella. It starts from minus infinity. And where does it end? N. So if N is here, what does that summation say? I'm summing all the delta L's from minus infinity to n, and including n. Is that clear? I'm summing all the values of this function from minus infinity all the way to whatever n is. In this case, I've drawn n to be a negative number. What do I get? 0. Okay? Now, what if n is here? I have a whole bunch of zeros and a 1. Right? When does, so u of n, whenever this n is negative, this diagram, which maps to that equation, tells us is 0, because I'm adding a whole bunch of zeros. Zeros. And the first sample n for which the summation becomes non-zero is where? 0. The moment I include this lollipop at the origin, this u of n turns into a 1 at n equals 0. And then this, when I go beyond 0, I'm just adding a bunch more zeros. Doesn't change anything. Reminds me of the Pakistani poet Iqbal. He has a little line of poetry. He says, if you add up the English paraphrasing is, if you add up the brains of 200 donkeys, it doesn't amount to the brain of a human. So this is the same story here. You add up a whole bunch of zeros, it doesn't add up to anything. But Iqbal never met the Dirac delta, which we'll come to later, which violates that principle. All right. So these are two different representations of the unit step and its relationship with the impulse. Now what I want you to do is write, or try to figure out how you can write the Kronecker delta in terms of the unit step. Can you do that? Can you fiddle around with the unit step? So now all you have in your toolbox is the unit step, and you can fiddle around with it. Can you fiddle around with the unit step? So you can scale it, you can shift it, you can do all those things with it, and create the delta function. And while you do that, I erase a few boards. Okay. Sarah, you get to pick the next person.
I choose last row, and shiny sunglasses. Green shirt.
Last row, shiny sunglasses. Ooh, green shirt. Huh? What's up is the delta and the U. No, what's your name? James. Okay. So you've got U of n. James has looked at U of n, okay, which is a bunch of lollipops starting at 0. And he's subtracting from that U of n minus 1. And how would I draw that, James? Shift the whole thing to the right by 1. So this one starts at 1. And the height of each lollipop is 1 on this side. So when you subtract this from that, you're left with a single lollipop at the origin, and that's the answer. Oh, yeah. Psh, psh. Well, you not getting sleep hurts you. My not getting sleep a crazy professor. I'm not the Unabomber, don't worry. Yeah, isn't that what yeah. Okay, we'll look at that as well. Let me just finish the story on this one. Delta of n being, I can write this expression, massage it in a very trivial way. U of n minus U of n minus 1 divided by 1, which is the distance between, which is the shift, essentially. This is sort of like a discrete time derivative. In continuous time, how do you compute the derivative? You look at a value here. So this is f of t. This is t. You look at the value at some point, and you look at the value at some adjacent point. So this is f of t. This is f of t plus delta. And you approximate the time derivative as f of t plus delta minus f of t divided by the amount of the distance between the two. Okay, and this is exactly what we're doing, really. You're looking at U of n, and 1 cent. So this 1 is that delta, adjacent value, divided by the shift. And you'll see this much more clearly when we go to continuous time. So the continuous time impulse is the derivative of the unit step in continuous time. Now, you had another characterization. Is it complicated? See, we want simplicity in this class. If you have a complicated expression, okay, what is it? U of n plus U of negative n minus 1. Does this work? So I hope you agree this is more complicated than the other one. Right. It's not that complicated, but it's more complicated. So, well, this is good practice. Let's see. U of n is like that. Let's put a question mark here before we...
U of f
This is u of n. So what is u of minus n? Opposite way. Don't take notes yet. Okay? So this plus that, what does that give you? So for n not equal to 0, because n equals 0 is their overlap. For n not equal to 0, what do you get? A bunch of 1s. And same on this side. Okay. At n equals 0, you get what? 2. So these are all 1s. And now you're subtracting the constant 1 from all of it. Yeah, that works. But this actually, yeah. Yeah. As you can see, there's a multiplicity of ways you can do this. The question, as will always be the case, is which one gives you more intuition about what's going on, and which one is more useful. Okay, this one has a nice interpretation that matches what you already know from your calculus classes. This is a discrete time derivative. It has a nice formulation. There are only 2 terms in it. Addition or subtraction is simpler than multiplication. This one requires time reversal and requires more additions and subtractions. So always pick the one that's simpler. We want crisp, clean solutions. And remember that on the midterm. Some of you discovered it crudely on the quiz. Yeah? That's why I put it in quotes. It's a finite difference. So numerical analysts call it a finite difference. And when you want to compute derivatives of continuous time functions on a computer, you obviously can't store all these values. You discretize, and then you take the difference and divide between adjacent samples, and then map it back to continuous time. If these samples came from time instants delta seconds apart, then you know what the derivative is. And you're right. If you have a discontinuity, you're going to run into trouble, and that's the trouble we run into in continuous time. Because the unit step in continuous time, the derivative at 0 becomes what? No, it's infinite. And that's why the Dirac delta in continuous time is infinite. Okay, go away. Good luck.